Hello, everyone, and thank you all for joining us today. I'm Bob Crossan, Senior Managing Editor of Water and Waste Digest. I'm pleased to be moderating this discussion today on behalf of Water and Waste Digest and our co-sponsor, Emerging Compounds Treatment Technology, or ECT2. I'd like to welcome you to today's presentation titled PFAS Roundtable, Industry and Regulatory Outlook. This PFAS Roundtable will be a data-driven, focused discussion involving recent industry case studies, remedial strategies, and regulatory vision for the future. Participants will gain valuable insight from a roundtable of experts discussing the latest real-world applications for remediating PFAS-impacted water. Geared toward environmental consultants and companies dealing directly with PFAS contamination, this panel discussion will offer data-driven science to help participants understand the importance of selecting the right technology for PFAS treatment and how to utilize regulatory drivers to choose the right solution for contamination issues. With the combined experience stretching over 6 decades, our panelists during this roundtable have been key experts in driving innovation and new solutions in the emerging contaminant world. We have some great speakers with us, and here they are. Steve Woodard brings over 33 years of experience in water and wastewater treatment to the ECT2 team, where he works as the president and co-founder. Currently focused on commercializing synthetic media technology targeting PFAS, 1,4-dioxane, specialty VOCs, and other emergency contaminants. Steve holds 10 patents for technology developed in the implementation of various systems and methods for treating water, wastewater, groundwater, and vapor, and he holds a Ph.D. in environmental engineering from Purdue University. Next, we have Avram Frankel. He is a professional engineer, technical expert, and program manager with more than 30 years of experience, including work on a wide range of commercial, industrial, municipal, state, and federal sites regulated under CERCLA, RCRA, TSCA, and numerous state programs. He has also spent a large portion of his career addressing emerging contaminants of the past and present, including hexavalent chromium, perchlorate, 1,4-dioxane, per and polyfluoroalkyl substances, and 1,2,3-trichloropropane. Lastly, we have Richard Hunter Anderson. He is an environmental scientist at the U.S. Air Force Civil Engineer Center in San Antonio, Texas. Dr. Anderson provides technical support and expertise to AFCEC's restoration program and serves as the Air Force liaison to SERDP ESTCP's Environmental Restoration Technical Committee. He received his BS and MS in environmental science from Oklahoma State University and Ph.D. in soil science from The Ohio State University. We will get started here in just a few minutes, but first a little housekeeping. You'll notice on your viewer that you will be able to ask questions. We encourage you to do so. We will get to as many as we can before the end of the presentation, and any questions we don't get to, we will try to answer offline. So with that, let's begin the discussion. I'll just kick it right off. There have been many technological advancements in PFAS treatment and how they can impact remediation strategies and tactics. But there's different technologies that have been more suitable for different types of contaminated water. When it comes to dealing with challenging water, what are the best strategies that you know of? I'll start this one off first with Steve, since you have such a wealth of experience in handling difficult water.
So, yeah, the difficult water, it's not always about just treating PFAS. It is often more important to understand what else is in the water and to apply the right pre-treatment and other approaches and technologies that will control fouling so that whatever media is removing the PFAS can do its job adequately. And I'm going to start with, I'm just going to go quickly through a few examples. The Stewart Airport and Air National Guard Base in New York State had a really challenging project where they collect spent de-icing fluid in lagoons, and then our job was to pump this de-icing fluid, which was also loaded with PFAS, through our treatment system and remove the PFAS before discharging to the public sewer. And so the biggest challenges there were very high iron concentrations, and then also propylene glycol. And so there were also solids and turbidity, but the challenge really became using, what we ended up doing was using a backwashable carbon or GAC system up front, preceded by oxidation to convert the iron to its insoluble form. And then we had to do a fair amount of work in the lab to find a biocide that would prevent the growth, the excess growth of biological organisms on the resin, which were performing the bulk of the PFAS removal, so that the resin wouldn't get fouled up and plug up and block the flow. And it was a real challenge to find a biocide that could do the job and not impact the ability of the resin to remove PFAS. So I think I like that example. Another one, we're working at a fire training school in Australia, where the influent concentrations are really high of PFAS, and we worked in the lab to find out that a coagulation, flocculation, sedimentation was the most effective step to reduce that upfront really high concentration of PFAS from the live fire training activities taking place. We have a site in Australia at the Williamtown Air Base where we're treating 3 different streams, one of which is stormwater. And stormwater is a real challenge because it changes almost daily, the water quality, and is, in this particular case, can be loaded with TOC and turbidity, solids, iron. And so we had to put in multiple stages of pretreatment, a rapid sand filter, followed by a backwashable carbon for TOC and some iron removal, followed by a specialized resin that allowed us to remove the rest of the TOC and the iron that was complex with the TOC. So again, and just one more quick example, we're also starting to work with landfill leachates where membranes such as nanofiltration and reverse osmosis are really, foam fractionation can also be used in some cases, but these matrices are very challenging to treat. And again, it's about the upfront pretreatment and protecting the resin so it can do its job, or the carbon, whatever's removing PFAS.
Yeah. Well, you noted carbon there. That seems to have been the standard and approved method for removal for a long time. But ion exchange has always kind of been in the midst there too. It's shown some benefits over carbon related to removal of all, including some small chain PFAS compounds. Longer life has smaller footprint as well. Why are ion exchange systems not more widely used in this treatment as opposed to, like, say, carbon?
It's a really good question, and the answer is that carbon has been around for a long time and has been approved for use, a best available technology in a lot of cases to treat a lot of different compounds. So the public is comfortable with it. That they're comfortable that their water is being treated by something that has been around and been approved for a long time. The people that select the technologies or specify the technologies have experience designing carbon systems, and the infrastructure is also out there. There are large companies that supply and change out carbon systems and regenerate carbon. So the technology's been around for a long time. It's not as specialized, or in many cases as well suited to removing PFAS as ion exchange resin. But hopefully I've provided some insight there. I definitely would hand it off to Hunter and Avram for their 2 cents, because I'm sure they run into this as well.
Yeah. Let's start with Avram.
Yeah, I mean, I agree with everything Steve said. I mean, it does, I think, matter whether we're talking, and I would add this to almost everything we're going to talk about today. Really, there can be a pretty significant distinction between, say, a remediation of a site and the water that would be generated there versus, say, a drinking water treatment application at a wellhead, let alone the things that Steve was just talking about, which are almost like waste streams versus, drinking water treatment at some point. But, yeah, I mean, I don't want to overstate the granular activated carbon, its history, and what's approved and not approved. I think what we're seeing is it is very familiar to the operators and the water companies. But as we're getting more and more, I think, into mixed contaminant situations, let's say volatile organic compounds or pesticides and herbicides plus PFAS, I mean, I'm definitely seeing that GAC is not necessarily the default setting anymore. And, ion exchange has made its inroads, especially becoming NSF certified, a number of years back. I'm seeing more and more openness to using that or other technologies besides GAC. So I think that's where we are with it. Things are shifting, and it's an education issue as well, and communication issue. I guess that's my comment on it.
Yeah, Hunter, do you want to add something to this as well?
Yeah, for sure. Thanks, Bob. First of all, let me just say thank you and hello, everyone. It's a pleasure to have this opportunity to pontificate on these issues. It's always fun. But with regard specifically to the market share of GAC versus ion exchange historically, I would just sort of reiterate what Avram just said about drinking water versus remediation. You've got to kind of keep in mind that for the vast majority of these examples that occur throughout this country where water in some capacity has been treated to remove PFAS, it's almost typically the case has been that these are time critical removal actions under CERCLA for drinking water wellhead type applications. They're not situations where you can study, best available technologies and pilot different technologies for a couple years before you arrive at an optimum solution. These are scenarios where you've got to have something mobilized within the month, or you're sort of culpable legally for some inaction. So really, at least within our portfolio, as soon as we discover these issues, it's a matter of contacting and mobilizing on what we call our rapid response contracts. Those contractors then have their sort of alliances with the various vendors out there, and it's really just a matter of what's been the case over time and who they've had relationships with. And of course, that's slowly changing, as the sort of number of case studies for ion exchange begin to increase. We generate the necessary performance data to kind of validate some of those default assumptions. But I would say in response to the initial question as well, it's definitely come to fruition at this point that there really is no silver bullet. I mean, maybe there's some more things you can generalize with ion exchange than you can GAC in terms of site-specific artifacts. But in general, the optimum long-term solution is going to be very site-specific, and that's going to depend on things like the water chemistry, the influent concentrations, what the flow rate demands are. I mean, if it's, if you're treating a 5 GPM well for a single residence versus million gallon per day, commercial utility, that's going to dramatically change how you think about technology selection. And at the end of the day, I suspect there's probably going to be combinations of technologies that ultimately prove the most optimal in any given site-specific application, such that these treatment trains are what we sort of start to think about. But just to reiterate, where we are, how we got to where we are now has really been the basis of emergency response actions, and it's just a matter of who the contractors have, on speed dial to mobilize. But after the smoke sort of settles on all that, all these exposures have been mitigated. We now get, an opportunity to kind of take a deep breath, look at those decisions, those remedies as they're developing or generating performance data, and take a more, methodical look at how these systems are performing, and if they need to be revised and redesigned, we will certainly do so.
I think another thing to remember is switching back kind of to the drinking water world, many utilities have GAC systems online already for taste and odor control or for some other contaminant. So they're already going to want to explore getting the benefit of treatment of PFAS with the existing system they've already paid for and know how to operate. So it becomes interesting when you get to a system that doesn't have a technology already there for removal of organics, and then what is the selection going to be there? But I mean, I think another thing, just to get back to the first question, just quickly, I want to really reiterate. I want to add to what Hunter said is, with all of these contaminants, whether it's PFAS or any other new thing that might come down the road, we have to stick with our, tried and true engineering principles, which is what Steve was talking about. We need to understand what the influent is. We need to understand what the flow rate is. We need to do all this upfront work. Where I see problems happen, whether it's PFAS or anywhere else with water treatment, is when we don't follow the procedures, the engineering procedures that we followed for decades to design effective treatment systems.
Mhm. Yeah, well, so it sounds like there's, like Hunter was saying, like kind of site specific, and sometimes the best option is kind of a series of things, or um, you have to kind of get a better understanding of it that way. How does one choose the best option then? Because like he was saying, there's a lot of things that kind of come into play there: life cycle cost, sustainability, waste liability. I assume, Avram, that you have a little more experience in this with consulting world and stuff. What are you seeing as repeat requests from clients and whatnot in regards to this?
Yeah, let me try to summarize a lot of things there relatively quick. I mean, it depends on the client, right? I mean, and let me just give you some examples. Some clients, and it depends on the challenge that a client is undergoing. Some clients do take a life cycle costing approach, and let me just define that. Really, just looking at capital and O&M costs without any other externalities is typically what I'm asked to do or I recommend. We can take that approach sometimes, and those clients maybe have a longer view, and that might guide the selection of one technology versus another. I would say that when we've done those for drinking water applications and some remediation applications, for a number of reasons, including the presence of short chain compounds, the ion exchange has come out as being the most cost effective technology on a life cycle basis. But you have other clients that Hunter was mentioning, like emergency response work, that are not taking a long view. They're on a 5-year horizon or a 2-year horizon or a 6-minute horizon or whatever it might be. We might, it might be what technology can you get in place the fastest. And then I just would add sort of the other client profiles. Some clients are more worried about long-term environmental liability and the risks and potential costs associated with that, and some are less concerned with that. They're driven by, not that they don't care, but they just are driven by other factors. I'll just give a good example of that from the real world. If you look at the public water supply world, you have some very wealthy utilities out there, and they have the means to be very aggressive to meet a particular challenge, PFAS being one that a lot of them have. So they will put a reverse osmosis system on there. They will do whatever they think they need to do because they have the luxury of doing it to essentially potentially over-design a system because they just want to make their ratepayers feel as comfortable as possible in their mind. But I also deal with, in the TCP world and in other worlds, you have a lot of utilities that are not that well funded. They are just trying to make it through the day and deliver water that meets state and federal standards to their customers. That's a different client profile. So we really need to come up with the truly most cost-effective solutions for them, and that's their biggest driving force. So just trying to paint a little picture there about client profiles to help with the discussion.
Yeah. So Hunter, obviously you're kind of more on that client side. What are the things that you're looking for when it comes to choosing the right solution for a project like this?
Yes, it's an interesting question, right? We've spent the last 15 years trying to get out of the business of installing pump and treat systems, moving more towards an in situ world for remediation. But here we are constructing them left and right for drinking water applications. But I'm assuming what will ultimately be the case, in terms of our circle of response, the permanent solution, a lot of these sites is going to be an above ground ex situ pump and treat, groundwater extraction treatments of some capacity. So you got sort of two elements to that. One is, what is that appropriate treatment train that best reflects the optimum conditions based on all the site-specific parameters that are, causal in terms of creating variability in performance. But also it is, as Steve alluded to in the very first question you asked, what within that fixed treatment train, what are some of those pre-treatment options that are going to preserve the longevity of whatever media and or treatment processes that you've selected over the long term. So if that's an iron issue, if that's a biological thing, and a best case scenario, you would study that in something like a feasibility study or an ECA or some kind of application where you would do some head-to-head sort of comparison. But also coming down the pike are a lot of different modeling tools again, as the number of case studies for all these different combinations of technologies and treatment trains emerge in the literature, we have an ever increasing resource to draw from in terms of how to forecast things like bed volumes, longevity, treatment media, regeneration effects, things like that. So it's really come to fruition that the more often you regenerate a GAC material thermally, there is sort of a loss on ignition and some degradation of performance. So you can kind of then forecast that 30 years down the road, and it looks pretty bleak at some point. So all of those things considered, your life cycle costs are going to dictate that optimum remedy. But that's not a trivial decision that can be made overnight. That's a fairly protracted, pilot study commitment. So this is sort of mutually exclusive to the drinking water application. Drinking water, for good, bad, or otherwise, it's just going to be the default thing the contractor's got to retain, or whatever vendor. Get the exposure mitigated, and then we'll deal with the consequences of all that after the fact, and we'll optimize down the road. But for these long-term permanent circular remedies for these contaminated AFFF impacted sites that we manage, it's going to involve a lot of study. And how exactly mechanistically that's going to take place, I think is still sort of subject to a lot of investigation. People have different thoughts, different modeling tools. The Water Research Foundation is producing some, life cycle cost comparison tools for different ion exchange media, different ways to combine those media with different pretreatment options to give you some forecast of longevity, things like that. But I also mentioned a collaboration with the EPA, and I'll probably address this later momentarily, so I'll just briefly introduce it now. But EPA's Office of Research and Development maintain what they call a drinking water treatability database, and forever it's been sort of just an online tool that water utilities and consultants and purveyors and whoever can go to and use just as a really high level kind of 50,000 foot desktop exercise to look at the effects of things like water chemistry, the flow rates, empty bed contact times, all the things you have to engineer around. You can kind of constrain that and use this tool to kind of then give you sort of a short list of what candidate technologies, depending on what types of technologies you're interested in, separation, destructive for different contaminants. Well, they've slowly started to include PFAS into this drinking water treatability database, and to do that, they've come to us as the owners of all these systems that have 2, 3, 4, 5 years worth of data at this point. And so empirically, we've been able to provide them with a means by which to really model different combinations of water chemistries and flow rates and empty bed contact times, primarily with GAC at this point, just because we don't have all the ion exchange data online yet, and it's hard to compile all that in the interim. But I think we've got a pretty good handle on GAC at this point, at least to say, initially, what are the conditions under which are going to impact performance? And you can kind of look down the road and say, well, my O&M portfolio would consist of this for GAC. And if you had some similar tool to give you those similar costs for ion exchange, or some combination of GAC and ion exchange, then you could just say it initially, well, these are the things we need to down select for a pilot study. Is this is what the data that's been published to date says about these technologies and these specific conditions. So it's a complicated question, but it's going to involve a lot of study to determine the optimum.
Yeah. Well, kind of getting back, let's get Steve into this as well. Since he works directly with the systems, he's pretty up to date on everything, I would presume, given his role. What do you feel are the best solutions for someone if they are looking specifically at life cycle cost?
Well, yeah, it often does, not surprisingly, boil down to life cycle costs, and I think both Hunter and Avram have done a nice job on this. So I don't need to spend a lot of time on it. The bottom line is that it depends on a lot of factors, and it's not a straightforward decision. You need to understand not only the influent flow, but the water quality. What PFAS compounds do you have? So what's the mix? What are their concentrations? What else is in there? We talked about iron and TOC and those things, but what about chloride and sulfate, other inorganic anions? A lot of these things can, in the influent water, can impact your technology selection. Also, what's the client looking for? What do they need? What regulation are they trying to meet? Or maybe they're even trying to do better than the regulation in their particular state because the users are demanding it. So really need to understand the ins and the outs. We also need to understand to select the technology, utility costs come into play, footprint, comes into play. What are the disposal options and costs associated with those options? There's liability management of the waste that's generated. So it's really quite a complex formula. We have our own model that is quite complex, and we don't. ECT2 doesn't install only resin systems. We've installed multiple carbon systems, and as others here have alluded to, a lot of times it's a combination of technologies. It's very frequent that we'll have carbon up front, often a backwash carbon, and then resin, maybe a regenerable resin, and even a polished single-use resin at the tail end. So yeah, it's the biggest mistake is to think that it's straightforward and not to do your homework or hire someone to do the homework to figure out, what technology under these set of conditions is going to have the lowest life cycle cost, because it's really important.
Yeah. Well, yeah, like given the concern of many regarding those life cycle costs for PFAS mitigation, I'm curious what everyone feels about the current status and best practices of residuals management for spent ion exchange and GAST. What are the biggest and current issues surrounding that? What are the advances in residuals management that you see over the next couple of years or so? Let's start with Hunter.
Yeah, sure. Okay. Well, so, I think it goes without saying that anytime you can concentrate, this waste stream into as small a volume, as concentrated of a small a volume as possible, you're better off in the long term, whatever your residuals management options are. It's certainly a lot easier to manage less of it than, more of it. So any technology that can concentrate it to the greatest extent, I think, is a front runner for ultimate application. But in terms of the options for the residuals management, look, incineration gets a bad rap, and perhaps so. I don't think it's gotten a bad rap for, out of precedent per se. It's not like, there's been volatile fugitive emissions from these incineration facilities that have impacted people. It's really just based on an abundance of uncertainty, some conservatism, and there's fairly vocal environmental, groups that have lobbied Congress for, rules and things that get tethered to our funding, and so we have to be cognizant of all that. As a consequence of all that, though, because it's largely driven by all this uncertainty, the DoD, through the CERTA and ESTCP programs that you mentioned earlier in my introduction, these are the research and development wing of the DoD, where we fund basic research under CERTA and applied research under ESTCP, basically to solve, environmental, issues and liabilities for the department. But because of all of these issues, we've put a significant amount of funding towards all of this incineration science. And it's not a question of whether or not PFAS can actually undergo complete mineralization, right, to fluoride and CO2. Well, I guess in the case of PFAS, it would be HF. But a complete mineralization is certainly theoretically possible. It's just a matter of under what conditions that occurs. So things like temperature, residence time, oxygen, that's what sort of remains rather nebulous in the R&D world. So all of these facilities that take, PFAS-laden waste and incinerate it operate under permits that are designed for all their legacy contaminants that, obviously they're compliant with. But the question is, are those requirements adequate to ensure complete mineralization of PFAS? And those questions just fundamentally aren't known, primarily because it's not an easy question to answer. There's not an error method, right? Just like for non-potable matrices of all sort, there is no standard EPA method, but for error matrix, it's even more nebulous because there's not even a consensus on the appropriate sampling train. Impingers, XADs, resins, nobody knows what these species consist of. If they are in fact perfluorinated, right, they would probably be associated with a lot of particulate material because they're, charged. But if it's the actual PFAS that's volatilizing is in fact non-polar, then you've got sort of other issues. Anyway, all of that science is sort of emerging now, and once we develop an adequate understanding of how to collect the samples, how to generate suitable and defensible mass balance data, we'll then have an ability to say something about the efficiency and effectiveness of incineration. Until then, we're just kind of at the mercy of the facilities that'll take it. If not the incineration facilities, then the only alternative is to landfill it.
Yeah. Avram, do you have anything to add on this?
I think Hunter pretty much covered it all there, but it's a significant concern for many of our clients. I wouldn't say all of them. Some of them are happy to have the GAC hauled off to thermal regeneration facilities or have ion exchange, incinerated and not think about it too much more. Others are very concerned about the ultimate fate. And, I think the air pathway is something that is not, it's been shown to be part of at certain industrial sites, it's been an issue. Just leave it at that. So, I think that's where the concerns come from when applying it to thermal treatment facilities. Hunter got into some of the real technical challenges of how do we get to the place where I think all my clients would like to be of when we send off PFAS waste of whatever sort, whether it's soil or ion exchange resin or whatever, that something can come back from the facility like we get for so many other contaminants of concern, a certification of destruction, or the stuff is in the landfill and we're all good. We're not there yet with the thermal facilities, and that's really a regulatory issue and a technical issue at this point.
I guess I'll also just mention real quick because the Chemours facility in North Carolina or wherever it is, by way of precedent, they've been disposing of a lot of material by deep well injection here in Texas. So, whether or not that continues to be something that people rely on or not, of course, the deep well injection, purveyors and vendors will tell you that that's safe. Environmentalists will tell you that it's not, and there should be, but definitely it's another option that's being utilized out there, at least to some extent.
Yeah. So
Could I
jump in
on that too? Yeah, well, one of the things that we didn't really talk about was on-site destruction, which solves a lot of these liability issues associated with landfills and thermal destruction. And there's a lot of good research going on, and some of it's being funded by AFCEC, where Hunter works. And the key to making these technologies work, and the technologies are plasma, low and high temperature plasma, electrochemical oxidations, senolysis, supercritical water oxidation, electron beam, etc. The key to making any of these technologies work is to reduce the volume of waste and thereby increase the concentration. And that makes these technologies now practical and amenable. And some significant progress is being made. I would say the low temperature plasma is showing the highest promise right now for being able to achieve complete destruction on site so that no waste has to be transported to a landfill or an incinerator. So I think there's a lot of excitement and focus on that these days, and there will be more moving forward.
Yeah, forgive me for not mentioning that. That's quite the oversight on my part. But yeah, I guess my interpretation of this discussion was what's currently the case for residuals management. But certainly it's all going to move to on-site. We've got a number of portable trailers that have been permitted now that are capable of destroying concentrated PFAS waste streams, at least in an aqueous matrix. But for some of the more solid materials, they can be slurried to some extent. But the aqueous world we've got a pretty good handle on. It's the solids world that we're still grappling with, for sure.
Yeah. So moving on more toward the regulation side of things, obviously there have been several states that have started to make their own regulations for this, and so the future is kind of changing in terms of regulatory framework. There could be some potential impacts to a variety of industries because of this too. So, for example, despite recent studies that provide evidence to the contrary, there are many regulating authorities that are moving toward regulating PFAS as a set or as a unit. So, for example, based on a sum total of select PFAS to include short chain PFAS. How would this affect the life cycle costs of an ion exchange versus GAC, assuming the same discharge requirements for the sum total are currently the case for PFOS and PFAS? Hunter, let's start with you on that one.
Yes, so this is a total game changer, right? I mean, if the situation weren't complicated enough just to think about PFAS and how you're going to effectively and efficiently remediate PFAS and undertake all of this rigorous decision logic, right, to arrive at some optimum solution. If you throw the short chain PFAS in the mix, it radically changes everything. It's almost common knowledge at this point, or at least it should be, that it's exponentially more difficult to remove the shorter chain PFAS from solution or from a solid matrix, regardless of the technology. They're just much less amenable to absorbent technology. Their affinities are just much lower for the solid phase. They're not as amphiphilic, so they don't partition to these interfaces that some technologies capitalize on, like foam fractionation, etc. But as a means to kind of forecast some of these potential liabilities, because we get questions all the time. We build these systems, right? We put them online. We're monitoring the discharge, and we're letting discharge and breakthrough occur up to, in what is typically the case, 70 part per trillion sum total PFAS, because that's this EPA lifetime health advisory that we're all sort of focused on as a de facto treatment target. So, we have sort of permissible discharge below that, and we get away with it because none of this is sort of legally required. We're doing all this under these voluntary, MOAs with different municipalities and what have you. And so the question comes up when we're building these systems, hey, why don't you be a little more conservative and just treat everything and regenerate your media or replace your media when there's first breakthrough? So as a means to kind of just get a first cut on what the implications are for our programming purposes for these systems, I mentioned that EPA drinking water treatability database a minute ago. We partnered with those folks down in Cincinnati at that EPA ORD office, who are the creators of this tool, and in sort of as a consequence of participating and helping them generate this tool with our data, they agreed to kind of do some modeling for us. And at least with respect to GAC, they forecasted what these breakthrough times would be under all these different combinations of scenarios. And then they have a cost module in that drinking water treatability database that uses all this work breakdown structure, and you can kind of constrain it and standardize things. But we tried to forecast what the out-year O&M requirements would be, the differences in out-year O&M requirements would be based on different scenarios where we're only treating PFAS and PFOA to the LHA, where we're only treating PFAS and PFOA to any observable breakthrough, or where we're preventing all breakthrough of all PFAS as modeled by the C4 carboxylate, which is the most conservative tracer that we currently have. And the results are striking. I mean, you're looking at least a threefold increase in O&M costs over the life cycle if you are inclusive of the short chain species. And I mean, propagated over the life cycle of these systems, that's an enormous bill. So if other technologies come online that can narrow the gap, like ion exchange, for example, in terms of what those additional costs would be to treat these short chain PFAS, if in the event we're forced to do so, that would be an absolute game changer and something we would have to consider.
Yeah. So bouncing back a little bit to this incineration side of things, removing PFAS forever seems to be kind of that next wave of concern for a lot of the parties involved. Burning PFAS in incinerators, like you mentioned, is one of the options there, but it could impact air, and burying it in landfills could affect the soil and whatnot. What other options are there available on that front in terms of the removal in that regard? And then, are you aware if EPA has a plan on this? And what about your clients? Like, what do they worry about in terms of environmental impact on this? Steve, do you want to take the floor on this one to start?
Yeah, I think I touched on some of the options already, but as far as EPA goes and having a plan, I'm not aware that they do have a clear plan, so I'd be interested in Avram and Hunter's opinion on that. And then, are the clients worried about it? Absolutely, they are. Some more than others, but yeah, when waste goes off site, let's say it goes to a landfill, where does that leachate end up? Right, it could end up being treated at a POTW. Where's the sludge from that POTW? It's quite it's quite a web when you find when you trace where the PFAS ends up, and who knows, maybe it ends up back in the landfill where it started, right? So the clients are concerned, and again, I think that's why there's such a push to develop a technology or really a conglomeration of technologies that are able to eliminate the need to transport PFAS waste off-site. At first, it seemed like this might be, this might be a pipe dream. It'll never happen, because you take these technologies like plasma and try to apply it to 200 gallon a minute remediation stream. It's just not practical, right? But if you can use like a regenerable ion exchange resin technology to reduce that several orders of magnitude, now you've got something that plasma system can chew on, over a longer period of time, and you can have multiple stages. And that's what we're finding might be the holy grail here in terms of eliminating that liability. But I'm interested in Hunter and Avram's take on this as well.
Yeah, Avram, let's start with you on that one.
Yeah, I mean, a couple of things, because I also think we kind of should revisit the regulatory question. But yeah, I mean, I think Steve's bringing a really important point. I mean, we know of examples. I can think of one in Southern California right now where you have a system, you have the PFAS that's being detected in a major surface water has come from the reinjection of treated water. Actually, water. It's wastewater that was treated to make drinking water that's reinjected into the ground as part of aquifer restoration, ultimate drinking water supply. Some of that ends up in the surface water, and that's where the background, or at least that's what is suspected as the background source of PFOA and PFOS in that system. And we're talking about a massive system here. So yeah, it goes without saying that there's a web there, and that's just one example. And that particular utility is actually engaged in one of the most comprehensive treatment studies for drinking water, that we know of. I know ECT2 is involved in that, and it'll be really interesting to see what those results are. But I want to kind of like back up to the regulatory question. This issue of, I think maybe it was overstated or to be understated, but what is driving these activities? I mean, we can drill down on all these topics and get super specific, but my clients are asking the fundamental question of what do we need to do in a given situation? And there's no federal MCL for PFOA or PFOS or any other PFAS compound. There's a small handful of states that have promulgated enforceable drinking water standards, some of which have lumped certain PFAS compounds together. Others are regulating individually. If you look at Michigan, there's a 6 order of magnitude difference in the MCLs for one compound versus another on their list. So that tells you right there that some states view different PFAS compounds as having very different potential effects on humans in drinking water. Other states, Massachusetts has got a proposed, actually promulgated standard that combines 5 different PFAS compounds. There's others, New York's got one that combines 2. So there's some radically different thinking going on there. So I think we got to be clear about that. And I think anybody in this business needs to really be paying attention to the background disagreements in toxicology going on that are, and the result of which is you see this difference in what is being promulgated, but also how few states have actually chosen to regulate PFAS or even are proposing to regulate. It's a little bit different realm in the groundwater protection world and in the surface water world, but it's basically the same story. It's evolving. But it really gets back to this question, at least for my clients, is what do I need to do? The presumption of needing to remediate, the presumption of needing to treat. I just want to be clear on this call, it's not always there. All right. This whole conversation is couched in the terms of, with the conclusion of we need to do something, and that what's triggering the need to do something is evolving as well because of the regulations.
Yeah. Well, in the interest of time, we're going to have to move on to the Q&A. I would love to continue this discussion. I think we could probably go on for quite a long time, but thank you all so much for giving this such insightful comments so far during the presentation, but we'll move on to the Q&A now.
Okay. So we have our first question here.
what are you seeing as the key decision criteria for selecting technologies for PFAS groundwater remediation and drinking water treatment services? Do you see the forces changing in the near term on that?
This is Steve Woodard with ECT2. Happy to take a first stab at this one. I think key decision criteria are beginning to focus more and more on life cycle cost and not just the capital cost. And that includes, as I mentioned briefly before, understanding the mix of PFAS compounds in the influent, including the short chains. And what are the effluent regulations you're trying to meet? What are the foulants and other co-contaminants, footprint available, and the requirements, utility costs, all those things. I think people are tending toward proven or at least demonstrated technologies, but for the forces that are changing, as we move into the future, there is definitely more and more of a focus on sustainability and waste generation. Where's the waste going? And that's where, again, the on-site destruction comes into play, at least for the groundwater remediation sites. And pretty excited about continuing to work with some key partners, mainly universities, to get to the bottom of nailing down on-site destruction, so no PFAS waste ever has to be transported off-site.
Excellent. So this one also is kind of directed toward you too, Steve. It says short chain and long chain PFAS removal was discussed. Steve, can you expand further about the comparison of ion exchange versus GAC regarding the removal effectiveness of both?
Sure. Yeah. I mean, in general, if you have a typical water, ion exchange, because of its dual mechanism of adsorption and ion exchange, does a much better job, has significantly higher capacity and faster kinetics for the short chains than granular activated carbon. The one exception is if you need to remove short chain carboxylates like PFBA or PFPEA or potentially HXA, and you have high inorganic anion concentrations in the water, chloride in particular, then ion exchange in that case may not be your best bet because the high chloride ion concentrations impact that exchange mechanism, which becomes all the more important as that carbon chain shrinks in size. So it's really dependent on what are you trying to remove, because if you're really looking at the longer chains like PFAS and PFOA, if that's your focus, then chloride concentration has very little to do with it. But it's all about the short chains and what else is in the water.
Got it. So a little bit more here included regarding ion exchange and GAC, mentioning that they're both decent technologies and they generally work. Getting concentrations down to 2 parts per trillion is difficult, but they can work. But the question is, but then what? Regeneration of GAC will produce a dirty gas stream. Getting PFAS compounds off ion exchange resins is also difficult and results in dirty water stream. They suggest that we need some newer and different technologies. Who would like to take a stab at this one?
I guess I'll jump in here. So this is Hunter. Look, they're the thoroughbreds of our industry at the moment, and I don't see that really changing anytime soon. But there are other separation technologies like reverse osmosis, and people are feverishly researching new ways to manufacture these membranes that are not only effective for PFAS but efficient, I would say. It's not a question of whether or not you can remove PFAS from an aqueous waste stream with membrane technology. It's just a question of how many are required and what the efficiency of that system is. But, I think in general, regardless whatever separation technology we ultimately land on is optimum for a given, set of site conditions and objectives, I think ultimately, we're stuck in this scenario where we'll have to simply concentrate the waste stream into as small a volume as possible to then, maximize our ability to efficiently manage the residuals. So I don't see separation technologies changing anytime soon. They're here to stay.
Got it.
I think I've jumped in on that as well. I mean, I think I agree with everything that Hunter and Steve have said. The thing I want to point people towards is really we have a lot of lessons learned from other contaminants. And I think one thing we're going to see, especially with these sites, not necessarily the sites with smaller plumes or really just soil contamination, not groundwater contamination, but for the larger plumes, it's combinations of technology, it's combinations of wellhead treatment, extraction and treatment perhaps, but also with in situ technologies. And we've done that successfully for PCE, TCE. I could, rattle off many other contaminants. We got to make sure that we apply all the lessons learned from the mega remediation sites and big groundwater management plume sites that we've successfully addressed in the United States and apply them to the PFAS problem and challenge. And that includes thermal technologies as well. So I just wanted to broaden that out a little bit more from just, water treatment.
Yeah. Well, we actually have a question here about the residuals management. It says, so there are only two methods of residuals management, incineration or landfill. And the question is hazmat permitting required for these?
So this is Hunter. I'm not entirely sure I understand that question, but I mean, if the residuals in question are exclusively contaminated with PFAS, I mean, as it stands, that is not a regulated waste, and by all accounts, legally, we would be allowed to simply throw it in the trash. But we go to the level of effort to ensure that it's managed in accordance with sort of a worst case, RCRA hazardous waste scenario. We, at least in AFCAC, our policies have always been to dispose of these materials in accordance with those onerous requirements, despite the fact that they're not legally binding. But I do think as new technologies come down the pike, incineration and landfilling will become less and less frequent. And I do think for aqueous waste streams, such that they are concentrated and low volume, that opens up the door for a whole variety of novel degradation, destructive technologies, to include those we've just discussed today. But I'm sure more are coming down the pike. For solid waste, it's a little different story and depends on scale. So if you're talking about large quantities of material, such that Avram was just referring to mega, remediation sites, we're kind of limited there with our available options, soil wash and thermal desorption, things like that. But if we're talking about relatively small residuals type material of solid nature, we can slurry it, and then that opens up options for things like supercritical water oxidation, hydrothermal treatment, things like that. So I think it depends on a whole bunch of factors for a given site as to what's optimal. But the number of options are increasingly becoming available as we move down the research pike.
Yeah, this is Steve. I agree with that, and I think, as far as I know, the only state that regulates PFOA, I believe it is, as a hazardous waste is New York State. I wouldn't be surprised if more states start to do so, or if ultimately it becomes a federally promulgated. But I don't know, Avram or Hunter, if you know of any others, but I think New York might be the only one right now.
Yeah, so I stand corrected on that. No, I'm not aware of any others.
Steve.
All right. Here's another one. What have you found for the capital and operational cost difference between granular activated carbon versus ion exchange? I assume Steve would be a kind of a start for this one, then we can go to the others.
Yeah. So on a unit cost basis, say per pound or per cubic foot, granular activated carbon is less expensive than resin. But if you look at, say, the empty bed contact time, you're not going to go with a residence time in the vessel or empty bed contact time for a carbon system less than 10 minutes, whereas with ion exchange resin, you're typically in that 2 to 3 minute range. So bottom line, if you're talking about single-use resin, you've got a media that's more expensive than carbon, but has much higher capacity and faster kinetics, so you use less of it. So the capital costs often tend to be a wash, and then it boils down to, what's going to last longer between the changeouts. And I would say in most cases, even with a smaller vessel and a shorter empty bed contact time, the single-use resin is going to last longer. So you'll have quite a bit lower O&M costs with the resin, and that's one of the things that I think people are starting to look more closely at. At first it's pretty simple for engineers just to look at the capital costs and compare them and pick one. But the fact is, these systems are going to be running for decades, and so it's really important to focus on things like getting the pre-treatment right, but then also understanding how that and everything else figures into the O&M costs. And that's also where the regenerable resin has a leg up too. You pay more to put that regen system up front on a capital cost basis, but especially for sites like source zones where they've conducted fire training, where you have higher concentrations, that payback can be fairly rapid if you're regenerating the resin in place and not hauling it away and figuring out how to dispose of it and then replacing it with virgin resin. So yeah, a lot to consider, but those are some general thoughts.
Yeah, I'll just add a little bit to that. Where we've done, it is very case by case specific. So, but where we've done life cycle evaluations, ion exchange has had the lower life cycle cost, and that's been very much enhanced if short chain PFAS are involved. But I want to point out another aspect that gets overlooked sometimes, is that one advantage of ion exchange is that, let's say you have a ion exchange and VOCs, very common situation. Almost all these PFAS plumes are commingled plumes, which also doesn't get talked about enough probably. But a big advantage of ion exchange is you can remove the PFAS and then use another technology for the VOCs or whatever else might be there that won't attach to the ion exchange. And that turns out to be an advantage in many cases, both on a technical basis and also with regard to legal settlements. So something needs to be considered.
Okay, I think that this will probably be the last question that we have for today because we're running out of time, but here it is. How are you addressing potential PFAS precursors that may degrade to PFAS during the treatment process?
Yeah, I'll take a quick stab at it and then hand it off for further comment. In the United States, at least up until now, precursors have not been taken much into account. In Australia, however, they are starting to look at the top assay, and it really muddies the waters, because what it means is, let's say some of the systems that we've been bidding on lately have been requiring TOPA down to low concentrations. And what does that mean? What that means is that there are a lot of precursors. They're not PFAS compounds yet, but under pretty extreme oxidative conditions, they can be converted into PFAS. So you may have a PFAS treatment system that perfectly well removes PFAS, PFOA, all the way down to the short chains, but doesn't remove some of these precursors because we don't even know what a lot of them are. They could be uncharged compounds. They could have ether linkages. They could be not removed well at all by carbon or ion exchange resin. And so then what happens is you take your sample, right, and send it to the lab, and you're non-detect for all PFAS compounds, but your TOPA result is quite a bit higher, and that's because these compounds, and we don't even know what they are, there's thousands of them, got converted in a laboratory under extreme duress conditions of high temperature and with high concentrations of really strong oxidants. And so it's a real challenge, right? Because it's this black box soup of compounds. We don't know what they are. So if you don't know what they are, how do you treat them? So some of the R&D that we're taking on right now, largely in Australia, is to try to get a better handle on what the compounds are, how to treat them, so that we can meet reliably low TOPA limits. But it really opens up a can of worms. And Hunter, I don't know if you or Avram have seen TOPA being applied as a standard in the United States yet.
I'll jump in here real quick and tell me, Bob, if we're overrunning. But, the good news is, at least with respect to the AFFF impacted sites, the vast majority of this quote unquote hidden mass, these precursors people talk about, are actually cations, and you won't find them in, the groundwater to any appreciable extent. But there certainly are other either, uncharged or anionic PFAS, the telomer sulfonates, for example, are pretty common. I don't think, these precursors are relevant with respect to our discharge requirements, what we're trying to treat. But to the extent that they do compete for some of the absorption sites for whatever, media we're using to absorb the PFAS of interest, that is, we need to be aware of that. So things like top assay and total organic fluorine, extractable organic fluorine, PIGI, there's lots of different instruments coming online to provide these surrogate measurements of total organic fluorine. But I think having an understanding of the influent loading is probably important in terms of how you design these systems. But I'm certainly not anticipating any requirements at the discharge for this hidden mass anytime soon.
Cool. So I have one question for the speakers. I can do one more question if you guys have time, but I want to be conscious of your time as well.
Sure.
Yeah, I'm good. Let her rip.
Okay, cool. So you guys had mentioned New York earlier. It says this question says that New York State recently adopted MCLs for PFOA, PFOS, and 1,4-dioxane. And based on the information provided by the New York State Department of Health, they have adopted GAC as the default technology and will require site-specific pilot studies to approve other technologies. So the question is, in the absence of federal regulation, how much is ECT2 working with state regulators to increase comfort level with ion exchange as a broadly available technology and viable technology?
Yeah, we are working with the state regulators. Here's the challenge, is that GAC is not very effective on 1,4-dioxane. GAC is effective on PFAS, obviously. We've been talking about that. And if you have high concentrations of 1,4-dioxane, then carbon has reasonable capacity. But down at these low ppb levels, the 1,4-dioxane tends to blow right through granular activated carbon. So it's a poor choice, frankly. I think the reason it was selected is because it can treat some 1,4-dioxane, albeit poorly at low concentrations, and it does do a decent job on PFAS. So there's some education that is taking place, but at the same time, ion exchange resin does not treat 1,4-dioxane either. So it's one of these cases that we've been talking about where more than one technology are necessary to treat these two distinctly different compounds with distinctly different characteristics.
And I'll just make a plug, my concluding remarks on that topic, and, I guess in general here, I strongly support the use of pilot studies anyway, and they don't have to be, major, large-scale investments. They could be, the rapid small-scale column experiment, type investigations. But comparing, the site-specific water of interest across different media is kind of a no-brainer, and I can't believe anyone would just blindly pick a technology without comparing and contrasting it against others quantitatively. I get the whole time critical thing, but now that that's kind of done and behind us, we're in a position where we can breathe and spend some time to make decisions during these evaluations, and we should be doing that.
That's a really, really good point.
jump in quickly before we end. I mean, it's a great question. I mean, and I do find it, I'm concerned about it because, I mean, I think outside of the remediation context, if you get in the hardcore drinking water treatment context, there's often not time for these pilot studies. So, or they have to be integrated like was done in Colorado with application, with the actual application. And that, you know, that has its challenges too. So I do think that education, it's not a criticism of anybody, but it does concern me because I think it's a bit of a regulatory laziness, to be totally frank, you know, on this. You know, ion exchange is a proven technology. It's NSF certified. There shouldn't just be this default to GAC without considering the, you know, other proven technology here. So that would be my comment on it.
Awesome. Well, I thank you guys all for being on this call today. It's been great to hear from you and get your insights and whatnot. We have so many more questions here, but we can't get to the rest of all of them. So I wanted to let everyone know that this is going to wrap up the question and answer session for the webinar, but questions that we didn't get to, we will answer offline. So on behalf of Water and Waste Digest and our sponsor, Emerging Compounds Treatment Technologies, or ECT2, I'd like to thank everyone for your participation today, and especially for all of our speakers and the great questions that we had come in. This webinar will soon be archived at the exact same URL that you used today to reach it, and you can find that on www.mag.com. It can be viewed on demand, so feel free to share this with others as they can also view it as well. So long, everyone, and take care.